Welcome back. Over the last couple of videos, we've been breaking down equation 2, or the MSA block, which is if we jump into here, this little section there, and equation 2. And we learned that equation 2 is actually comprised of a few other equations that were introduced in various papers, such as attention is all you need, which again was by a team of researchers, and layer norm was itself introduced in a research paper. So it's understandable if you're not quite sure what these actually do to begin with, because we've only covered them very briefly. So if you'd like to learn more, there's resources in the book. Otherwise, you can definitely search it up. But now it's time for us to start writing code. So let's just write a doc string here. I issued you the challenge in the last video to give it a go and see if you can create a multi-head self-attention block. I trust you gave it a shot, but let's now do it together, hey? So creates a multi-head self-attention block, which is MSA block for short. So if you weren't quite sure like what KQV means in multi-head self-attention, might make a little bit more sense once we code it out. You know the motto, if in doubt, code it out. So to begin with, we're going to initialize it. Now we need an embedding dimension here with 768, and then we need a number of heads parameter, which is going to be an int. This will be the number of self-attention heads. So I'll write this down here, heads from table 1, and this is embedding, or the hidden size D, that is, hidden size D, embedding dimension. We already know that from the parameter name, from table 1 for vit base. And I'll just write here as well, this is for vit base. And we'll go down here. We also need a parameter attention dropout. This is a little bit hidden in the paper, but nothing you can't find with a quick little search. So if you search for dropout and label smoothing, dropout, we actually find that there's no dropout used with the attention. So we kind of had to wait all the way to Appendix B to find this out. So as I said, papers are just treasure trails of different information. Dropout, when used, is applied after every dense layer, which is in our case going to be within our MLP layers or our linear layers, or dense layer is another word for, there's actually like 4 or 5 different names for a dense layer. You could call it fully connected, you could call it linear, you could call it forward, feed forward or something like that, except for the KQV projections. So this means dropout, when used, is applied for every dense layer except for the KQV projections. Now, where have we seen KQV projections? We've seen it here. KQV. We haven't seen this in, QKV. It's quite hard for me to read that. QKV projections. So that means we're not going to use dropout in our attention layers, according to the paper. And directly after adding the positional to patch embeddings. Oh, we haven't done that yet. We might have to do that later on when we create the full VIT architecture. But let's not stop there. We've got embedding dimension, number of heads. What is number of heads? Well, this is the H dimension over here. When we say multi-head attention, there's just regular attention, scale dot product attention. Multi-head attention splits this equation across multiple dimensions, hopefully giving it more learning opportunities. And I say hopefully because a lot of this stuff is sort of, you're thinking that it will work, and then you kind of have to test it to see if it does. You can theorize it that it will, but until you actually try it out and then publish a research paper with your results and going, hey, this actually improves things, you don't really know. So that's the H dimension here, number of heads. And if we jump back into the paper, a lot of jumping around here, but this is kind of what you have to do to replicate a paper, is that we have vit base, attention heads is 12. And then we're coding it in such a way that if we wanted to upgrade it to 16 for the other model variants, we could definitely do that. Whew. So we've initialized our MSA block. What do we do next? Well, let's create the norm layer, which is, if we jump back to the keynote, which is this one, we're going to create the norm layer first, layer norm, ln, and we can do that in PyTorch using what? Layer norm. So our layer norm layer is going to do what? It's going to normalize our input values across the dimension that we pass it. The normalized shape equals embedding dim. How do we know that? Well, if we go to the PyTorch documentation for layer norm, do you see what we're doing here? We're slowly breaking it down, and I've said this a few times now, we're breaking the architecture down into single layers as much as we can. So norm is just one layer in PyTorch, applies layer normalization over a mini batch of inputs as described in the original paper. Here's the equation that it does. So the output of the layer normalization layer is this, x minus all this jazz. I can't even read most of these. I like to learn things with code instead of trying to read math symbols. The mean and standard deviation are calculated over the last d dimensions, where d is the dimension of normalized shape. So normalized shape here. We've got epsilon value. I think that is mentioned in the paper as well. So if we go epsilon, I don't think it is, maybe. So this is the thing, right? A lot of hyperparameters aren't actually mentioned, but they're just inferred. So if you find that, please let me know. But what a lot of layers often have by default is a pretty good value to begin with. So we're just going to leave this as it is. Let's jump back into here. There's our layer norm. And now let's create the multi-head attention layer. You know, you might have tried this out yourself. So MSA, multi-head self-attention layer is self.multi-head attention. We could call this whatever we want, really. I'm just calling it that. Now we're going to do nn.multi-head attention straight from PyTorch. So thank you, PyTorch team, for implementing this. I was getting ahead of myself. So this takes an input parameter of embedding or embed dim, and I've called ours embedding dim, which is this. And then we take num heads, which is going to be number of multi-headed attention. That's where the H dimension comes into here. Then what else do we need? Well, there's a dropout parameter here. Now, the paper doesn't mention using dropout on the attention layers, but I've put it in here anyway. So if we did want to try it out later on, we can do so. And then there's one final parameter, which is batch first. And I'm going to set that equal to true. Now, where could we find out what that parameter does? Of course, in the documentation. So if we come here, we've got embed dim. So what's our embedding dimension? How many attention heads do we want? What's the dropout? And then a whole bunch of other parameters that I'll let you research. And then we have batch first, which is false by default. So if we come down here, so if true, then the input and output tensors are provided as batch, sequence, feature. Is that what we've done? So I just want to copy this because this is another little confusing thing about machine learning and deep learning is, again, different names for the same thing. The default is false, so the sequence comes first, then the batch, then the feature. So what is our input to block 2, to the MSA block? We've embedded our patches, and we're going to put the output here of this equation into this equation. So what is the shape? We're back to input and output shapes once again. We have a look here. Our patch and position embedding shape is going to go into this block. So what is the dimensionality here? We have batch, number of patches, embedding dimension, or in PyTorch terminologies, if we come back here, batch, sequence, feature. So let me just write this down. So I'm going to write, is the batch first? Question mark. Batch, sequence, feature, which in our case is batch. And then we have number of patches, which is our sequence of patch embeddings. And then feature is our embedding dimension. So sequence, short or SEQ, short for sequence. In our case, we have a number of patches that are in a sequence, and feature, which is another word for, say, learnable features. So we want learnable features of a sequence. And in our case, we're calling that embedding dimension. So there's some terminology there for you. Now, if we keep going, we've got 2 layers. What do we have to do next? Once we've instantiated some layers, we have to define a forward method so that we can say, how does the computation flow through these layers? So here is another little tricky part. But if we jump back, we've got embedded patches, X comes in, goes through the normalization layer. That's pretty straightforward. But then here is the multi-head attention part. This is a little bit tricky, but we know that it's going to take in query, key, and value. So if we jump into the documentation, the forward method takes in a query, key, and value. Now the tricky part here is that all of these are the same thing. That's where self-attention comes. Remember when we described self-attention or multi-head self-attention? Is which part of an input sequence should pay the most attention to itself? We're not going to define this. The network is going to learn this on its own. So we just pass in 3 versions of the sequence as the query, key, and value. And by going through these equations, and if we go to Appendix A, we can see here, by the query, key, and value, going through all of these steps here, our network is going to learn which part of a sequence should pay the most attention to itself. And inherently, if it learns that representation, or if it learns which sequence should pay the most attention to itself, hopefully it learns a good representation. So let's see what this looks like in code. We're going to do the norm layer first, layer norm. Just pass X through that. And then we're going to go here, attention output. And I'm going to do an underscore here because the PyTorch attention layer outputs an attention output and attention output weights. So we don't actually need the weights. We just want the activations out of the layer. So I'll let you read more into what the outputs of the weights will do if you'd like. So in this example, they're creating a multi-head attention layer with embed dim and number of heads. And this is just showing how to get the output. You pass in a query, key, and value, which is exactly in line with what the paper is saying here. 3 heads or 3 inputs, query, key, value, or QKV. So let's jump in, go back to code. So I'm going to take our multi-head self-attention layer. So multi-head attention. Oh no. Multi-head attention. That's Codelab saying, hey Daniel, you've spent too much time explaining and not coding. I know, you're right. So there's a query, key, and value is equal to X. And do we need the weights? I'm going to say false because that is that underscore there. And if we jump back in there, it's going to output the attention weights. That is that parameter there. If specified returns attention output weights in addition to the attention outputs, default true. I'm setting that to false. Okay. Now let's return the attention output. So have we just replicated equation 2? So a fair bit of explaining there, or 2 videos worth of explaining, maybe more, but we've just replicated the entire MSA block in 24 lines of code, and we could actually do less if we got rid of the comments. So that, my friends, is equation 2. We go right back up. A lot of information here. But we've just replicated equation 2. So we've got MSA wrapping the output of a layer norm that takes the input of a previous layer. Now, there is one part we haven't included though. That's the skip connection here. So I want you to have a think about how we could put the skip connection into this, but we're going to use that later on. And you'll see when we create the overall transformer encoder, which is this here. When we create this, we'll implement the skip connection there. But what we've done is now we've got this and this in a reusable piece of code. So in the next video, we're going to practice using this layer and we'll see what the inputs and outputs look like. So have a think about how we could create the residual connection. And if you want to jump ahead, create an instance of this block and then pass our patch embedding through it and see what happens. I'll see you in the next video.